Hi everybody, and welcome back to CHMP 442 Quantum Mechanics. And let's continue to take a look at how we can visualize these solutions to the Schrödinger equation for the hydrogen atom, given that we have a radial expression, a radial solution, and a spherical harmonics solution. So how do we visualize those all together? Let's take a look. So life was pretty easy when we were considering the s orbitals. These were orbitals that were spherically symmetrical. So what happens when we consider the p orbitals? Well, there are 3 p orbitals for each n when n is greater than or equal to 2. So again, we recognize that when L is not equal to 0, therefore not the s orbitals, then the wave function psi is not spherically symmetric. So let's consider the angular parts. Therefore, when L is equal to 1, we have 3 spherical harmonics that we care about. And we can look at the simplest one first. And going back to our material from chapter 6, we recognize that the y function in here is 3 over 4 pi. Square root of that term in brackets multiplied by cosine theta. And again, what is theta? Theta is our north to south angle, right? So when theta equals 0, we're pointing in the north direction. Cosine theta is equal to 1. And when theta equals pi, so 180 degrees down, again cosine theta is equal to -1. And so in the Pogel exercise that you may be aware of right now, we're aware of these tangent sphere pictures, and I'm going to show you those. These are the tangent sphere pictures that come from Macquarie textbook, figure 7.4, and we're familiar with these particular descriptions of the p orbitals. What we must notice is that the radial functions are not included. Loosely speaking, the orbital shown as the p sub z orbital corresponds to the description of the y01 wave function, the spherical harmonic associated with that. But let's remind ourselves what the wave function is, psi 210. So we'll see, of course, that we have this exponential decay piece, and we have this polynomial term in here that get added to the cosine theta spherical harmonic, the function associated with the angles theta and phi. In this case, it's just theta. We'll get on later to a more complicated picture when we come to look at the phi part of the angular piece of the solution to the Schrödinger equation for the hydrogen atom. The point here is that these are the angular parts, and that this is a real representation as opposed to an imaginary. There's no complex number description embedded in these particular images. But in reality, what we need to do is be able to recognize a visual representation of the actual full wave function to the Schrödinger equation, which also includes this radial piece. Let's take a look. So the Macquarie textbook provides us with some images of the actual wave function, and at the top here we see the wave function, and in the lower set of images we start to see the wave function squared. So these are called surface plots, and what we start to see is the 2 lobes in the 2pz wave function in here. Well, what we start to see is that that wave function decreases exponentially as we go out towards r equals infinity. We can see that there are the two lobes in here. One has a positive value, one has a negative value as we move in different directions around or away from the nucleus. Of course, when we take the square of that wave function, we can look at the probability density, and that's shown in this second line of images. So this is a good way of demonstrating the wave function. It can get quite complicated, but I'd now like to switch gears a little bit and look about how we can present the same wave functions perhaps as a probability density plot. And the idea here is that we divide the space into little volume elements, and we ask the question what the probability density for any given volume element is, and we can actually plot a density of little dots in a certain area to represent the probability density in that particular volume element. Again, let's look at this as a picture, and it's easier to explain. As described a second ago, these little dots in here, and the density of those dots is proportional to the probability of finding the electron in that region. So of course, as we go further away for the 3s orbital, we'll find that the density of dots decreases. The other thing that's interesting from this particular way of demonstrating the wave function is that the color changes depending on whether the wave function is positive or negative, even though this is actually a probability density plot. So we're communicating a little bit more information rather than just the probability density. Of course, this makes sense if we look at the 2p naught orbital that's shown in here and we compare it back to our earlier surface contour plot image. And here's the image I was referring to. So I've been talking so far about orbitals where m sub l was equal to 0, and I've approximated that as the p sub z orbital in the case that l is equal to 1. But it's harder to draw the orbitals when m sub l is not equal to 0, because now we have to include the phi term. And so on the left hand side of the picture here, I've got all the orbitals, all the complete hydrogen-like atomic wave functions, and what we'll see is that we've got these phi terms now, and in this particular case we've got this e to the plus or minus I phi term in here. So what does that even look like? So there are two ways of showing the wave functions. The wave functions as calculated are complex. Therefore they have these I values in them. But if we remember that the energy is only a function of n and l, so for example y plus 1 and y1 and y minus 1 and 1, so these two correspond to the same energy. They correspond to the same energy in the solution to the Schrödinger equation. In both cases the theta term is the same, and in both cases the radial function is the same. So what we can say, if we go back to earlier chapters, is that any linear combination of y1 plus 1, any linear combination of these two functions is going to be an energy eigenfunction. What does that mean mathematically? What it now means is we can write the following expression: p sub x equals 1 over root 2, and we can similarly write an expression for our p sub y orbital. So these end up being linear combinations in here, linear combinations. So by choice we can then replot the linear combinations, and these linear combinations, these end up being real, right? There are no imaginary numbers in these expressions, and they have rather convenient directional properties. So again, we're going to notice that the p sub x orbital, that's going to be aligned along the x-axis, and the py suborbital, that's going to be aligned along the y-axis. And so let's take a look at these real functions in table 7.5 and see how they're different with the functions that are shown above in table 7.3. Let's have a look. So if we can compare and contrast these two tables, it's interesting to look at the psi 100 function in here and the psi 1s function. Because they're spherically symmetrical, they're identical. In fact, if we look at all of the top three functions, they're completely the same as the functions in table 7.5. Where of course there's a difference is where we have these functions where there is an imaginary component. And in fact, all of these terms now are rewritten. If we look at the expressions that we see in table 7.5, we see things such as psi 3px, whereas on the left hand side here we see psi 311. And so that's the difference. Where you see psi 3px or 3py, psi 3py, these are the real parts, these are the real solutions. Real meaning there is no imaginary component to them, and they've been conveniently selected so that we can see the wave function point in a convenient direction that aligns with the x and the y axes in particular. So let's have a look at those images. Well, before we look at the actual images, let's look at the equations that we use to derive those images. And in fact, these are the angular portions of the wave function. So this is for the situation where L is equal to 0, and that means that the quantum number m sub L is either 0, plus or minus 1, or plus or minus 2. There is no imaginary part to the angular part of the wave function for which m sub L is equal to 0, but the latter four equations that are shown here for 7.32 from the textbook, these latter four equations have been modified so that we're only seeing the real portion of the angular wave function. And it's these five equations that are going to be demonstrated in the following graph. So here are the three-dimensional plots of the angular part of the real representation of the hydrogen atomic wave functions as described in the caption, and this is for L equals 2. So these are the d orbitals. One thing that you can notice is that the magnitude of quantum number m sub L is equal to the number of nodal planes that contain the z-axis. So for example, if we look at the d sub yz component, we see that there is a nodal plane here that kind of sits in between the lobes. There's a similar nodal plane that exists for the d sub xz orbital. So there's only one nodal plane in each of these cases, so these particular wave functions are associated with m sub L is equal to 1. You can easily see that there are in fact two nodal planes that exist for the two orbitals that are shown on the left hand side. So that completes our review of the shapes of the orbitals and how we typically only see the angular part of the real representation of the hydrogen atomic wave functions in most of the images that we see, mainly because of the complexity of the wave functions, the complexity of those wave functions in the psi form that include the radial part. So we'll move on from this topic. See you in the next video.